In this video, we're going to look at the remainder theorem for Taylor and Maclaurin polynomials. So, first off, what is the remainder theorem for Taylor and Maclaurin polynomials? The remainder theorem for these polynomials will give us a function, so the function will be r sub n of x, which is going to be sort of the remainder of the series for the polynomial, either Maclaurin or Taylor, of degree n. That's like degree n. Okay, so pretty similar. I'll show you what they are. I'll give you an outline of deriving it, even though it's not going to be completely rigorous, and then a couple examples. But here's what they are. So for Maclaurin, the remainder will equal the n plus first derivative of the function evaluated at some c, it's going to be in the interval, I'll tell you in a second what the interval is, divided by n plus 1 factorial times x to the n plus 1. And this is going to be for some c between 0 and x. 0 and x in this case because Maclaurin polynomials are centered at 0. And then Taylor is very similar. So Taylor remainder theorem, r sub n of x is equal to the n plus first derivative evaluated at some c, and this c is going to be between a and x. A being the center of our Taylor polynomial, divided by n plus 1 factorial times x minus a to the n plus 1. So here's what they are, and before I go over a quick derivation of them, just the idea is, in the nth degree Maclaurin polynomial, or Taylor polynomial, we take care of all of the derivatives up to the nth derivative. And that's going to be over n factorial times some sort of nth power of x. What we're missing is the n plus first on, and this, or this, depending on which polynomial we take care of, considers those derivatives. This, for some c, isn't just going to be a single value. It could be any number of values in there. And so it's not just going to be, well, it's going to be one term, but it says, okay, I can have something here that takes care of the rest of it. So let's do a quick derivation. And the idea, now this isn't perfect, but the idea is this. If I have my original function and I subtract off, I'm going to do this for Taylor polynomials, so Taylor polynomial of degree n, there's going to be something left over, and I'll make it of the form k times x minus a to the n plus 1. Now, in here, this is an nth degree polynomial, so if we take n plus 1 derivatives, this is going to go to 0 at the n plus first derivative because we keep on taking derivatives, but once I get past that nth power, it goes to 0. I get the n plus first derivative of f, And that's going to equal, and when I take n plus 1 derivatives of this, it's going to be n plus 1 factorial times whatever this sort of coefficient or whatever is here. And I'll solve for k. So k is going to equal the n plus first derivative of x over n plus 1. And it's going to be, to actually get it to work out, instead of having to deal with one thing but deal with everything, we're going to consider that this x is somewhere in this interval. We're going to get this down, so that means that the remainder, when I do subtract these polynomials, will be this, where I replace the k with this term at some c in that interval over n plus 1 factorial, because I would divide both sides by n plus 1 factorial, and then multiply it by x minus a to the n plus 1. Now, okay, so for some c in between, or in 0 to, sorry, not 0, a to x. Now, you can see this makes some sense. The biggest issue with this right now is just sort of a little bit of the hocus pocus to get from here to here. There are plenty of more rigorous proofs online, but for matters of explanation, this should make some sense. That, okay, if I take my function and subtract off the approximate polynomial of nth degree of something left over, and if I take some derivatives, I'll get to this form. And so that something left over has to be this for some value of c. Let's see how this is used. Again, if you want to have a full rigorous proof that also explains why that x goes into a c, look online. So finding the remainder of a third degree Maclaurin polynomial for f of x equals sine x. Now, before I even go on, not necessary for this problem, but recall that the third degree Maclaurin polynomial for sine of x is going to be x minus x cubed over 6. Now the remainder, we just need a few pieces here. So I need the next derivative, the fourth derivative of x. I actually only put that c in there, divided by n plus 1, so 4 factorial, all multiplied by, and since this is a Maclaurin series, x to the fourth, and the fourth derivative of sine, well, it goes sine, the first derivative is cosine, the second derivative is negative sine, the third derivative is negative cosine, and the fourth derivative is back to sine. So the remainder of this will be the sine of some c divided by 24 times x to the fourth for some c between 0 and x. And why I keep on saying between instead of writing an interval is I don't know if x is positive or negative. So if I put the interval from 0 to x and x is less than 0, it's not a valid interval. Okay, so there is the remainder for that Maclaurin polynomial. And now let's look at a remainder for a Taylor polynomial. And this one I'm not going to put down the fourth degree Taylor polynomial. It's not necessary. Not hard, but it's going to have a bunch of e's. It's going to be a lot of time. But the remainder, so the remainder for this will equal the fifth derivative of some c in a to x divided by the next factorial, 5 factorial, times x minus my center to the fifth. And now I need to get to the fifth factorial. So we have e to the negative 2x the fifth derivative. The first derivative is going to be negative 2 e to the negative 2x. It's chain rule. The second derivative is going to be positive 4 e to the negative 2x. The third derivative is going to be negative 8 e to the negative 2x. The fourth derivative is going to be 16 e to the negative 2x. And the fifth derivative is going to be negative 32 e to the negative 2x, which means that my remainder will equal negative 32 e to the negative 2c over 5 factorial multiplied by x minus 1 to the fifth for some c between 1 and x. Alright, I hope that helped out. The next video coming up is going to be an explanation for Lagrange error bound, which is very closely related to this, so I'm going to use this in that. Feel free to comment below if you have any questions.